Let's imagine we're looking at an unsigned integer y that's a non-negative counting number, 0, 1, 2, all the way to infinity. Let's choose one of those. And then let's try to write that in our three representations that we've been studying. We said that the decimal representation, aka the base 10 representation, expresses the value of y as multiples of powers of 10, where the decimal digit in position k is aligned with or multiplied by 10 to the power of k. So d0 is multiplied by 10 to the 0. d1 is multiplied to 10 to the 1. And then we go all the way up to the nth digit in position n minus 1, and that's multiplied by 10 to the n minus 1. Remember, the subscript value corresponds with the power of 10 in that representation. When we use a binary representation of the same unsigned integer, the underlying value is identical, but the way that we express it is different. Specifically, we use binary digits or base 2 digits. We call those b sub n minus 1, b sub n minus 2, all the way down to b0. The same rule holds where the value of the subscript represents the power of 2 aligned with that bit. So b0 is multiplied by 2 to the 0. And then we add that to b1 multiplied by 2 to the 1, plus b2 multiplied by 2 to the 2, all the way to the mth bit, which is going to be b sub m minus 1 multiplied by 2 to the m minus 1. Of course, we also saw the same idea in hexadecimal representation, where each hexadecimal digit tracked scalar multiples of the corresponding base 16 raised to the power. In this video, we're going to focus on the translation between decimal digits and binary digits. Specifically, we're going to ask ourselves, for any unsigned integer, how many decimal digits are necessary and how many bits are necessary. We're going to come up with a distinct formula that allows us to calculate a priori the number of decimal digits we might need versus the number of binary digits we might need. Let's start by looking at our decimal representation, and we'll ask ourselves a question: which unsigned integers can be represented by one decimal digit? In this case, of course, 0 requires one decimal digit, and then 1, 2, 3, 4, all the way till we get before 10. What's the largest number before 10? It must be 9. It's the one less than the base by definition. In other words, the set of all numbers that can be represented by a single decimal digit accurately start at 0 and go up to 9. And of course, 9 is 1 less than 10 to the first. That naturally leads to our next question: which numbers do we represent using 2 decimal digits? Notice that instead of the single d0, we now have 2 digits right next to each other, d1 and d0. The smallest number that we would need to use 2 digits for is 10. Specifically, notice that the number 9 does not require 2 decimal digits. We can write it in 2 decimal digits. Of course, 9 is always equal to 0, 9, but we're claiming we don't get any extra information from that 0. So we can drop that and it goes down to the 1 case. The first non-trivial example where we need 2 digits is the number 10. That's the minimum value where we require 2 digits to represent it. And then the maximum value would be 99, because if we go one more, we actually need a third digit. Remember, 99 base 10 is the same thing as saying 10 squared minus 1. Let's keep going with our analysis and ask ourselves, when do we use 3 decimal digits to store numbers, or what numbers can be stored using 3 decimal digits? The first interesting case really happens at 10 squared, or 100. If a number is less than 100, we can actually express it using 2. So let's take the number 67. We could always write 0, 6, 7, but the leading 0 does nothing to encapsulate values, so that would be a 2 decimal digit number. On the flip side, 100 is the lowest value. It's the minimum value that actually requires all 3 digits to store that number. Then we can count upwards, 101, 102, and just keep going. And the last possible digit, the maximum value that we can store using 3 digits, is going to be 999, or another way, that's 10 to the third minus 1. Now I'm going to ask you, do you see a pattern here? When we have 2 decimal digits, numbers that are expressed using 2 decimal digits really range between 10 to the first, less than or equal to d1, d0, that's any number that has 2 decimal digits, and then that's strictly less than 10 squared. And the reason we say that it's strictly less than 10 squared is the largest number that can be stored using 2 decimal digits is 99, which is exactly equal to 10 squared minus 1. Of course, 10 squared minus 1 must be strictly less than 10 squared. So indeed, that upper bound holds. When we think about 3 decimal digits, notice that that's going to come in the form d2, d1, d0. The first case that's interesting is really 10 squared. So those are bounded below by 10 squared. And then we can go no larger than 10 to the 3 minus 1 in terms of integers. The moment we drop to 10 to the 3, that actually requires 4 decimal digits. So we know immediately that the set of integers that require or can be expressed exactly using 3 decimal digits is bounded below by 10 squared, bounded above and strictly less than 10 to the 3rd. Before we show the next row in this table, let's see if you can intuit or guess what the lower and upper bounds are going to be. So if I ask you the question, which numbers require 4 decimal digits to encapsulate accurately, or which numbers can be accurately written using 4 decimal digits, could you guess the lower bound on that? Well, let's see. The lower bound on 2 decimal digits is 10 to the 1. The lower bound for 3 decimal digits is 10 to the 2. What's the lower bound for 4 decimal digits? Well, we would guess that maybe it would be 10 to the 3. 1 less than whatever number of digits we have. And that kind of makes sense because 10 to the 3 is 1 followed by 3 zeros, which is indeed 4 decimal digits. How about the upper bound? What's the first number that cannot be accurately represented using only 4 decimal digits? Well, for n equal 2, that is 10 squared, because 100 actually requires 3 decimal digits. For n equals 3, that's 10 to the 3rd, because 1000 requires 4 decimal digits. So let's see, 2 goes to 2, 3 goes to 3. Could you guess what 4 goes? Yep, you got it. This would be strictly less than 10 to the 4th. Or in human language, what's the largest number that can be represented accurately with 4 decimal digits? Well, that must be 10 to the 4th minus 1, which is 9999, or 4 nines altogether. This leads naturally to my challenge to you. Could you come up with the smallest number that needs 5 decimal digits to represent? Well, what did we see? 2, the smallest number, was 10 to the 1st. 3, the smallest number, was 10 to the 2nd. 4, the smallest number, was 10 to the 3rd. So 2, 1, 3, 2, 4, 3, 5, 4. You got it. So this is going to be 10 to the 4th. What's the other side of that bound? What's the smallest number that cannot be represented by 5 decimal digits, that requires an extra digit? Notice that answer for the other ones, 2, 10 squared, cannot be represented with 2 digits. 10 to the 3rd can't be represented with 3 digits. 10 to the 4th can't be represented with 4 digits. So that would mean what? Yep, 10 to the 5th cannot be represented with 5 digits, because that's 1 followed by 5 zeros, which is 6 digits. Now I ask you, can you generalize this? Can you go from a specific value of n to a general value of n where n is greater than or equal to the number 2? So in other words, if I tell you the number of digits you're allowed, can you tell me the minimum and maximum values for the type of numbers that can be stored exactly using that number of decimal digits? Well, what we saw is that for the minimum value, however many digits we have, that's going to be 10 to the power of those number of digits minus 1. So in the case of a general n, this would be 10 to the n minus 1. And then we said that the upper bound for that would be 10 to the n in those situations, which is exactly the pattern that we saw. And in fact, that's what we see here on screen, that when we have n digits, the general form is as we expect from these videos. And then the minimum value is 10 to the n minus 1. And the maximum, the absolute upper bound, would be 10 to the n minus 1, which is another way to say that we will never actually be able to encapsulate 10 to the n using n digits. Remember, the major question that we're asking ourselves is, if we have an unsigned integer that is greater than 0, how many decimal digits do we need to encode that unsigned integer? We're going to come up with a formula to actually give us an answer to that question. And that formula comes from the realization that any unsigned integer that is not equal to 0 sits between 2 powers of 10. On the lower bound, we'll say that it's 10 to the n minus 1, where n is the number of digits that we need. And we'll say that that's going to be less than or equal to 10 to the n quantity minus 1, which is strictly less than 10 to the n. That is the inequality that we've just generated in that table. Remember from our previous lives in mathematics, though, we actually know how to undo this exponentiation. We know how to get rid of the base by applying a log function. Moreover, log is a monotonically increasing function. In other words, if I apply a log to every single individual entry in an inequality, as long as the entries are positive, the log maintains that inequality. That's what we say when it's monotonically increasing. We will actually give a formal proof using calculus-based methods later in this video to justify that I can take this inequality, apply a log to every quantity 1, 2, and 3, and the inequality holds through the log. Log is an increasing function. That's another way to say that. But remember, when we take log base 10 of 10 to the n minus 1, the log base 10 and the base 10 cancel out, and I'm just left with n minus 1. In the center here, I have log base 10 of my unsigned integer n, which I was looking to consider to begin with. And on the right-hand side, I have log base 10 of 10 to the n. The log base 10 and the base 10 cancel out, and I'm just left with n. Now all of a sudden, I have this representation where the number n is an integer greater than or equal to 1, which means n minus 1 is an integer greater than or equal to 0. This could be an integer or a non-integer. The only way that log base 10 of n would be an integer is if n was a pure power of 10. Otherwise, it's going to be a non-integer. And then we know that that will be less than n. Notice that log base 10 is stuck between two integers, n minus 1 on the bottom side, where this is less than or equal to log base 10 of n. And then on the upper bound, we know that log base 10 of capital N is strictly less than the integer n. But remember, that implies immediately that if this is in between two integers, it could be the lower integer, the one towards negative infinity. It will never be the upper integer. If we take the floor function of that, it will always get mapped to the integer less than that. In other words, n minus 1 is going to be equal to the floor function of log base 10 of capital N. And another way to say that is the number of digits used to represent uppercase n in decimal representation is given by the formula the floor of log base 10 of capital N, the number we're trying to encode, plus 1. Let's go ahead and code this up in MATLAB and see what we're talking about. So we'll say capital N is an unsigned integer. Let's start with an easy one, 584 perhaps. And then we'll say that lowercase n is going to be equal to the floor of the log 10 function of capital N. And then of course we have to add 1 to it because that's what our statement says in this formula. If we were to run this code, notice that lowercase n is going to be 3. In other words, the number of decimal digits used to represent the number of 584 is 3. That's exactly what we see, 584. This formula gets really interesting because right now I've actually written the exact form of this as an unsigned integer in decimal notation, but I could write this as a computational expression. For example, what if I wanted to know how many decimal digits are required to express 2 to the 24th? When I push enter, MATLAB says 8. And in fact, if I take 2 to the 24, notice that I have 2, 4, 6, 8. That's exactly what this formula is telling me. I now know that if I want to know the number of decimal digits required to represent a number n, this formula will give me a closed form solution to that. Let's keep going and check an interesting case. Let's figure out how many decimal digits are required to represent the number 10 to the 3 minus 1. Well, remember 10 to the 3 is 1 followed by 3 zeros, so that would be 1,000. 1,000 requires 4 decimal digits. If I subtract 1 from that, 1,000 minus 1 is 999. So I'd expect that number to be 3. Indeed, when I run that code, that's exactly what this formula produces. That in order to encode 10 to the 3 minus 1, I need exactly 3 digits. On the other hand, if I take that negative 1 out and I run it again, notice that I need 4 decimal digits, which is exactly what we expect. 1,000 requires 4 decimal digits. With that, we have a closed form formula that discusses the number of decimal digits that we need to represent any unsigned integer. We're now going to generalize that to figure out how many bits are required to represent any unsigned integer using binary representation. And literally the work that we're going to do is a generalization of this decimal formula that we just generated. Let's get insight into that larger question by studying some base cases. We'll start with the easiest or least complex. Let's ask ourselves the question, how many different numbers can be encapsulated in a 1-bit binary representation, or a 1-digit binary number. We know that the smallest value that can be represented by 1 bit is 0. So if that bit was 0, that would represent the number 0. And then the largest value is 1, since 1 in binary is identical to 1 in decimal. So the maximum value that can be represented by 1 bit is 2 to the first minus 1. Let's go on to the question about how many numbers can be stored in 2 bits. In this case, the smallest number, the minimum value that can be represented in 2 bits, is the number 1, 0 in binary. So 1, 0 in base 2 is equivalent to 2 to the first in base 10. And that's because if I'm anyone less than 2, let's say that I was 1, I don't need 2 bits, I only need 1 bit. So the minimum value for 2-bit binary number is 10 in binary, 1, 0. In decimal, that would be 2 to the first, which is just 2, of course. And then the absolute largest value is 1, 1, since we max out that number when the most significant bit is 1 and when the least significant bit is 1. That value 1, 1 in binary is equivalent to the value 2 to the second minus 1. Well, 2 to the second is 4, minus 1 is 3. 1, 1 is the value 3 in binary. So from that standpoint, we say that 1 bit encapsulates the numbers 0 and 1. 2 bits starts at 2, goes up to 3. How about 3 bits? Well, 3 bits, we would say that the first number that really can be represented using 3 bits, or the minimum value in that encoding, would be 1, 0, 0. If I was anything less than 1, 0, 0, I wouldn't need 3 bits. I could do it in 2 bits. But if we see this, remember that each binary bit is a placeholder. So B sub 2 gets multiplied by 2 squared. B1 gets multiplied by 2 to the first. B0 gets multiplied by 2 to the 0. If I have 1, 0, 0, that's 1 times 2 squared. 0 times 2 to the first. 0 times 2 to the 0. In other words, that's the number 2 squared. So the minimum value that we need 3 bits to encode is 2 squared. The maximum value, what happens when I max out each individual bit, which is the chain 1, 1, 1. So here we have 1, 1, 1. That's equivalent to taking 1 times 2 squared plus 1 times 2 to the first plus 1 times 2 to the 0. So that would be 4 plus 2 plus 1. 4 plus 2 plus 1 is 7. 7 is another way to say 2 to the third minus 1. 8 minus 1 is 7, and that's exactly what we see here. If we think about the 4-bit scenario, if I want to capture which numbers are expressed using 4 bits, here 4 bits I have B3, B2, B1, B0. The first number that we would need 4 bits to encode would be the binary number 1, 0, 0, 0. So that would be B3 has a 1, all other ones are 0, but remember B3 is associated with 2 to the third power. 2 to the third power is 8. So the first integer that we need 4 bits to encode is the number 8. We get up to the maximum value for 4 bits when we max out each individual value, which happens in the bit string 1, 1, 1, 1. And that's what we see here. But remember, this is 1 times 2 to the third, 1 times 2 squared, 1 times 2 to the first, 1 times 2 to the 0. So that's 8 plus 4 plus 2 plus 1. 8 plus 4 is 12. Plus 2 is 14, plus 1 is 15. 15 is 16 minus 1, or 2 to the fourth minus 1. Before we drop down to row 5 of this table and ask ourselves what numbers can be stored using 5 bits, let's go back and look at the last few rows. So we said when m is equal to 2, if we have a 2-bit binary number, the smallest number that we can represent with 2 bits non-trivially is 2 to the 1. In other words, 10 base 2. Moreover, the largest number that can be represented is 1, 1 base 2, or 2 squared minus 1. So the smallest number is 2, the largest number is 3. Well, we know that 3 is 1 less than 4, so we're bounded below where this is a less than or equal to by 2 to the first. We're bounded above by a strict inequality by 2 squared. If we have 3 bits, notice we're bounded below by 2 squared, because the smallest number that requires 3 bits is 1, 0, 0 in binary, or the number 4. And then we know the largest 3-bit binary number is going to be 1, 1, 1, which is 7. So 3-bit binary numbers start non-trivial at 4, go up to 7. In other words, these 3-bit binary numbers are definitely less than 2 to the third, which is 8. When we look at m equal 4, which numbers are encapsulated using 4 bits? The smallest 4-bit number, the one that requires actual 4 bits to encapsulate, is 2 to the third, which is 8. In binary, that would be 1, 0, 0, 0. And the largest 4-bit number is 1, 1, 1, 1, which is 15, or 16 minus 1. In other words, this 4-bit string is strictly less than 2 to the fourth. Well, do you notice a pattern here? When m is 2, the number of bits is 2, I see that it's bounded below by 2 to the first. So let's see, 2 goes to 1. When m is 3, it's bounded below by 2 to the second. 3 goes to 2. When m is 4, it's bounded below by 2 to the third, so 4 goes to 3. Could you guess what happens when m is equal to 5? Let's see, 2 to 1, 3 to 2, 4 to 3, 5 to 4. You got it. So this would be 2 to the fourth. How about on the upper bound? Well, let's see. 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 must go to 5. So now we know all of a sudden that all 5-bit binary numbers are going to be found between 2 to the fourth and 2 to the fifth. This, of course, assumes that the leading bit, the most significant bit, is non-zero. Otherwise, we could drop back down to a lower row. That is indeed what we have in our table. And now I ask you the question. What if we were to just do this for a general value of m? What are the lower and upper bounds for an m-bit binary number? Well, let's take a look. 2 went to 1, 3 went to 2, 4 went to 3, 5 went to 4. So m, could you guess? Yeah, that's it. This would go to 2 to the m minus 1. How about the upper bound? Well, we see 2 went to 2, 3 went to 3, 4 went to 4, 5 went to 5. M must go to m. And now all of a sudden we have a range for the numbers that can be accurately encapsulated using m bits in binary. This observation that an m-bit binary number, if the first bit is non-zero, the value of that number is going to lie between 2 to the quantity m minus 1. And at the upper bound, the biggest m-bit binary number is going to be 2 to the m quantity minus 1. Well, we can translate that into the following inequality. If I have an unsigned integer, capital N, and I'm going to represent that using m binary digits, I immediately know that capital N lies between 2 to the quantity m minus 1 on the lower bound, and that's a less than or equal to sign. And on the upper bound, the biggest m-bit binary number is 2 to the m minus 1, which is strictly less than 2 to the m. Specifically, it's 1 unit less than that. Just like we did in the base 10 case, we can actually bring the exponent down in front or eliminate the base using logarithms. In this case, instead of log base 10, we're going to use log base 2. I'll take log base 2 of this entire inequality, this term, and that term, claim log is an increasing function. So if we look at the way log actually behaves to the right of the y-axis, it actually increases. So log will preserve the inequality symbol, just as we've seen here. And log base 2 of 2 to the m minus 1, the 2's cancel out and I'm just left with m minus 1. Log base 2 of n doesn't change because I'm not really sure what n is, and it's not clear that this is easy to simplify. But on the right-hand side of this inequality, log base 2 of 2 to the m, the 2's cancel out and I'm just left with m. m minus 1 is an integer. M is an integer, so now log base 2 of capital N is greater than or equal to the integer m minus 1 and strictly less than the integer m. The fact that log base 2 of capital N is between two integers and bounded below by m minus 1 immediately means when I take the floor function of log base 2 of n, that is going to be equal to the biggest integer that is less than that number always. So m minus 1 is equal to the floor of log base 2 of n. But that means that the number of binary bits can be written by the equation floor of log base 2 of n plus 1. So if I want to know the number of binary bits needed to represent an unsigned integer n, this formula will give me that number. And in fact, I can confirm this formula in MATLAB. Specifically, we're going to go ahead and define the variable m to be the floor function of log base 2 in this case, not base 10, because we're not asking how many decimal digits, we're asking how many binary digits. So the base in this logarithm is 2. And then we put an n on the inside of the argument to the log and then add 1 to this. Now, all of a sudden, if I were to ask myself, how many binary digits are needed to encode 10 to the third or 1,000, the moment I run that, I see that m is 10. Another way to say this is if I were to take des2bin of the number 1,000, that outputs a string where this is the binary encoding of the number 1,000. And then of course I could just take the length of that and notice that it is 10 characters long, which is exactly what my formula m equals the floor of log base 2 of capital N plus 1 is telling me. Let's try a different situation. In this case, we'll take a look at the number 2 to the 24. That is 2 multiplied by itself 24 times. Remember that in decimal, if I had 10 to the 24, that would be a 1 followed by 24 zeros, which would be a total of 25 digits. In binary, this is the exact same structure. It's going to be a 1 followed by 24 zeros in binary, so we expect that to be 25 bits. On the other hand, n, the number of decimal digits, is 8, and that is because when I actually take a look at that number, there are 8 decimal digits. Of course, we could confirm that our formula for m works out by taking the length of the output of des2bin of that number, and again, that is 25. On the other hand, if I were to actually just subtract 1 from that, my claim is the moment I subtract 1, I'm going to go from a 25-digit number to a 24-digit binary representation. When I push enter, clear the screen, and check m, indeed that's 24. If I were to take des2bin of the number n, this is going to be 24 ones all put together. This formula for the number of bits required to encode an unsigned integer capital N really came from this inequality bounding any natural number between 2 powers of 2. Another way to say this is that any unsigned integer, any positive whole number, can be put between 2 powers of 2. So let's take the number 6, for example. 6 can be found between the number 4 and the number 8. That is what this inequality is saying. If we take the number 1,000, 1,000 is between 512 and 1024 on the upper bound. 512 is 2 to the 9th. 1024 is 2 to the 10th. The moment that we know those bounds, we know that the number 1,000 is going to be encapsulated using 10 binary digits, because this inequality really tells us a direct relationship between the size of our unsigned integer and then the number of bits needed to encode that in binary representation. We claimed that we could actually simplify this math by applying the log base 2 to the entire inequality, and that would maintain the direction of those inequality signs. And my claim is that that's actually a lemma. In fact, the reason that this log function maintains those inequalities really has to do with the behavior of a log function. If we remember, logarithms kind of have a vertical asymptote at 0 and then go off to positive infinity as we go to the right on the x-axis. And in fact, the domain starts at 0, doesn't touch 0, and goes off to infinity. And on that domain, it is a monotonically increasing function, which means as I move to the right in my input, my output grows. We can formalize that observation in a lemma, which is like a mini theorem that we use to justify that this math is actually true. To start this lemma, we'll say that a is any positive integer that is bigger than 1, and then we'll look at the function f of x equals log base a of x, and our claim is that that function is increasing. And what we mean by this is if x is less than or equal to z in the domain, then f of x is less than or equal to f of z in the range. In other words, indeed, inequalities maintained in the input stay the same direction when we apply the log to that inequality, which was the fundamental idea that we used to create the formula for the number of bits necessary. In order to prove this lemma, we're going to go back to single variable differential calculus. If you remember from that course, we had a theorem that connected the behavior of the derivative to the behavior of increasing functions. Specifically, we said that if a function has a positive derivative at some input, then that function is increasing at that point. So in other words, when we look at this function f of x equals log base a of x, if we can prove that the derivative of that function is positive for all input values x, then we know that that function is increasing, and we know that this inequality will always hold, which means we can actually use that in the way that we did to generate those formulas. So our goal in this justification is actually to show that the derivative of log base a of x is actually positive for any positive natural number a that's bigger than 1. To do that, we're going to use something called implicit differentiation, which is a technique that allows us to take the derivative of an implicitly stated function. Specifically, remember that in logarithmic notation, we said that if y equals log base a of x, we could write an implicit relationship between x and y using exponent notation. So this statement, y equals log base a of x, is equivalent to the exponential notation a to the y equal x. In other words, when I take log base a of x, I'm asking the question, what do I have to raise a to in order to get x out? So y is the value of the exponent. Then when I take a to that value, I get x out. Remember, the whole goal of this justification is to show that the derivative of y is a positive number for all values of x that we're interested in. So we'd like to actually differentiate both sides of this. Taking derivatives of exponents is actually not so easy, but remember, if we were to do some algebraic simplification and apply the ln function on the left-hand side and the ln function of the right-hand side, the derivatives of ln's are a little bit easier, especially when we're looking at some of the algebraic simplifications here. So ln of a to the y is equivalent to y times ln of a. That's a constant. On the other side, we have ln of x. When we take the derivative of both sides, now we're taking the derivative of y with respect to x. There's a scalar inside. And on the right-hand side, we're taking the derivative of ln of x. Remember, when we take the derivative of a variable times a constant, we can pull the constant out. That's called the constant multiple rule. On the right-hand side, the derivative of ln of x is 1 over x. Then we can continue with two algebraic simplifications. Number one, let's pull this constant over to the other side of the equation. And then number two, let's look at the derivative of y as a symbol of hope in the city of Gotham. This is just a symbol that represents our desired derivative. So specifically, we now have a closed form way to state the derivative of our function y, which is given by 1 over x times ln of a. But remember, the goal of this argument is actually to say that this derivative is positive. And in fact, if we look at any natural number that's bigger than 1, the ln of that number will also be greater than 0. So that's a positive number. 1 divided by a positive number is also a positive number. And then we know for the input of log base a of x, x has to be greater than 0 and can go all the way up to infinity, which means on the domain points that I care about, x is always positive. So I have a positive times a positive. That's a positive. 1 divided by a positive is a positive, which means all derivatives to our log base a of x functions are positive. But the moment that we know that y prime for our function log base a of x is positive, by our theorem in calculus, we know that y equals log base a of x is increasing. And the moment that we know that that function is increasing, if we take x less than or equal to z in the input, we immediately can conclude that log base a of x is less than or equal to log base a of z, which is the exact property that we use to transform statements about exponents into statements about the number of bits that we needed. We just applied log to this chains of inequality and then maintained the directions of those inequalities. That concludes the tutorial portion of this video, where we've actually seen for any unsigned integer, we now have closed form formulas that tells us the number of decimal digits that we need. That's given by the floor of log base 10 of that natural number plus 1. And then we also have a closed form formula for the number of binary digits needed to write the binary representation. In this case, it's the floor of log base 2 of capital N plus 1. This leads very naturally into today's community challenge. Specifically, we use the table on the left to generate a general understanding of the lower and upper bounds for the numbers that are encoded in an n decimal digit representation. On the table on the right, we used our explorations to see lower and upper bounds for the types of numbers that can be encoded using m binary digits, m bits in a binary representation. Our community challenge for today is, can you use these explorations to generate similar lower and upper bounds for a hexadecimal representation? And using those upper bounds, can you generate a closed form formula for the number of hexadecimal digits needed to encode any positive unsigned integer? You can write your answers to this community challenge problem in the section below, or a link to other people that have answered this question. Of course, I always welcome your questions, comments, concerns, and feedback. When you give me feedback, I grow my brain. Thank you so much for your attention, and I'll see you in the next video.